Okay. Good morning, everybody. It's a pleasure for me to introduce Luca Mariotta, that you already probably know, because he's always here.
Yeah. I'm always here. Somehow I'm lingering.
And he has made a double degree PhD here in Bicocca and at the University of Nice, France. And after that, he spent a couple of years here as a postdoc student. Then he moved to Radboud in the Netherlands, and finally in Twente,
Yeah.
where he is currently an assistant professor.
Yeah.
And in the talk that he will give us today, he will provide an answer to a very nice question, that is, are cellular automata of any use to cryptography?
Okay. Yeah.
Thank you.
Thank you, Alberto, for the introduction, as always. So let me first change the scene here. Otherwise, the recording will be botched in the end without slides that are showing in the video. So thank you all for being here. And yeah, so the questions for today is to understand whether cellular automata, which are like a famous computational model for modeling a lot of complex systems, are actually of any use to cryptography. And it is basically a reflection, let's say, of my last 10 years since I started like doing research on this topic in particular. My PhD was on cellular automata-based cryptography. So this is mostly to see like what are my insights that I gained in these 10 years, because it seems that so there is like kind of a disconnection between like the publication that you see there are explicitly mentioning cellular automata for cryptography, and usually you see them like after a certain while, after a certain year, they start to be published only in venues that are not related to cryptography, but rather only related to cellular automata, natural computing, evolutionary computing, and so on. And cryptographic venues that apparently they are still using cellular automata, but actually they are calling them in different ways. So there is this sort of disconnection, and this talk is also to understand like how to bridge, let's say, these two communities, and what are like my let's say, opinions about these strategies for bridging the two communities. So, of course, I need to focus the slides here. So I will first start with a brief introduction about the design of cryptographic primitives and cellular automata, just to give the basic building blocks that we will be talking about in this talk. So, in particular, here we are focusing on symmetric cryptography, which is the setting where you have two parties, Alice and Bob, who wants to securely communicate between each other. So in particular, you want to enable confidentiality of messages exchanged between Alice and Bob, which means that they are using a channel that you see here in the center of the slide that is intercepted in theory by an adversary who is, I don't know, called Oscar, for example, as opponent. And it can basically read everything that is passing through the channel, okay? Then it can also do like more sophisticated attacks like tampering with the messages, like modifying them in transit, but we are mostly focusing only on the basic attack where it can just read everything that is going through the channel. So what Alice and Bob are doing is to agree on an encryption and decryption function, which are basically considered to be public, so also known to an attacker. The encryption function is used to, let's say, encrypt the plaintext message, PT, and then you obtain a ciphertext, CT, which is, let's say, sent to the channel, and Oscar cannot like see what is the original meaning of the message of the plaintext. On the other hand, Bob will use like a decryption function, which is performing the reverse transformation, so recovering the plaintext PT from the ciphertext CT. Of course, this is all the security of this system is relying on the fact that Alice and Bob are also agreeing on a so-called secret key, which is the same both for encryption and decryption. So it is given as an additional input to the encryption function and the decryption function, and it is the same. So this is the reason why this is called the symmetric cryptography. Then there is also public key cryptography, which we are not concerned about here, where you have like different keys for encryption and decryption. But okay, we will mostly focus with cellular automata that are used for symmetric cryptography, so for this setting here. Basically, when you see symmetric encryption functions and decryption functions, or ciphers, let's say in general, you have two settings in cryptography. So you have the setting of stream ciphers and the setting of block ciphers. So in stream cipher, usually you have an initial, let's say, secret key, K, which is, let's say, stretched, expanded in a key stream, Z, by means of a so-called pseudorandom number generator, or PRNG, okay? And then finally, when you have a key stream, which is of the same length as your plaintext that you want to send to Bob, for example, then you perform as an encryption function simply a bitwise XOR. So bit by bit, you go with the bits of the plaintext message, you XOR it with the corresponding bit of the key stream. On the other hand, in block ciphers, the situation is a little bit different because you are considering your plaintext message as a whole, and then you chunk it like in small blocks of a fixed length, let's say. And then each of these blocks are undergoing, like this block here, are undergoing different, let's say, sequence of transformations. So you have usually a confusion phase, like this one, and then you have a diffusion phase, which is like in this P box here. And finally, you mix everything like the result of these two operations in sequence using an XOR with the so-called round key. Now here I'm being like intentionally generic, and then later we will go a little bit more into the details of this confusion and diffusion operation. But let's say that the main difference between these two settings is that here, basically, in stream ciphers, you are encrypting, let's say, one bit at a time, okay? While here, you are encrypting one block at a time, which could be way larger than a single bit, let's say. The upshot is that when you are designing a symmetric cipher, be it stream cipher or block cipher, you need a lot of low-level primitives where you are grounding your security claims, basically. And these low-level primitives are, for example, pseudorandom number generators that we have already mentioned here for stream ciphers. They need to satisfy some security properties. You need Boolean functions. You need S boxes, which are basically vectorial Boolean functions. You need permutation or diffusion layers, which are these P boxes that I mentioned here for block ciphers, and so on. So we are composing them as a Lego, let's say, construction, all these low-level primitives, in order to have like a design such as the design of the stream cipher that you see there on the left, or the design of the block cipher that you see on the right. Now, what are the approaches to actually choose these low-level primitives? So the traditional approach is that you employ specific algebraic constructions to choose certain primitives that are satisfying by design security properties such as resistance to linear cryptanalysis, to differential cryptanalysis, and other type of attacks. So all these constructions are in a sense ad hoc. So you are considering like a specific example, and then you prove like the security properties on top of these specific examples. Then there is what I call the artificial intelligence approach, somehow, in the sense that instead of using ad hoc algebraic constructions, then we are supporting the cryptographer, the designer of a cipher, in choosing among different primitives using AI methods or models. They are coming usually from these two following domains. So deep learning here has nothing to do. So this is a part of artificial intelligence that has usually little relevance in the design of a symmetric cipher. So usually we employ AI methods from the domain of optimization, like evolutionary algorithm, swarm intelligence, and so forth, or computational models, for example, cellular automata. To a certain extent, also neural networks have been used, but not in a machine learning way, so rather as a computational device. Here, of course, we are going to focus on cellular automata. So what are cellular automata, more specifically now? We consider the setting of one-dimensional cellular automata, or CA for short. And basically, you can consider them as a massively parallel computational model that is composed of a finite array of cells. So for instance, if you have n cells, like in this example here, each of these cells can be in a state either 0 or 1, okay? And then each cell is updating its state by looking at its present state, so its current value, and the value of some of the neighboring cells, okay? Here, specifically in this example, we are considering a cellular automaton of diameter 3 and offset omega 0, which means that each cell is looking at itself, so this one, for example, and then at the two right neighboring cells, so on its right here. So this neighborhood here, 1, 0, 0. And then you compute a local rule, which is common among all cells. So this f here, you compute it. This is basically a Boolean function, and then you substitute the output of this Boolean function as the next state of your cell here, and then you continue like this. So here for the second cell, you will shift like one place to the right, and then you apply. You want to compute the output, the next state of this cell here. So you will compute f of 0, 0, 0 because the diameter is still 3, and you want to check like what are the two right neighboring cells. And then you continue like this. Then there is the problem that at a certain point you will hit the end of your array because it is finite, right? So there are two possibilities here to deal with cells at the boundary. The first one is the no boundary CA, which you see here on the left. So basically here we say we just discard the rightmost cells that do not have enough neighbors in order to compute the local rule, which means that here we will have an output which will be shorter than the original input, right? Otherwise, you have periodic boundary conditions for cellular automata, or PBCA for short, which means that you consider the initial vector here as a ring, as a kind of a circle, and then the basically the right neighbors for these last two cells here corresponds to the first two cells on this other part. So it's just like a circular buffer in a sense. Okay, so what are the motivations for using this simple computational model for defining like symmetric ciphers? Well, the idea is that we have two properties that are appealing about cellular automata. The first one is the, let's say, argument of security from complexity, because cellular automata, when you iterate them, especially in the periodic boundary condition settings, so you iterate them for multiple time steps, you can see like very complex and sometimes beautiful patterns arising depending on the initial conditions that you set in the initialization vector, and also depending on the underlying local rule, so the Boolean function that is determining the next state of the cells. So complexity is nice because we can use this in order to compute like cryptographic primitives that have like strong security properties. So the more a cellular automaton is complex, let's say this is very intuitive and not very formal, but let's say the more it is complex, the more it is difficult for the opponent, for Oscar, to predict, let's say, what is the next value for the cellular automaton, and so also to break like the cipher, basically. The other nice property of cellular automata is efficient implementation, being a massive parallel computational model, because each cell is like updating its state in a parallel fashion. Then basically you can leverage this parallelism to and the locality of the cellular automaton, also the fact that each cell is just looking at a certain number of neighboring cells to compute its next state. You can use this parallelism to basically achieve the so-called lightweight cryptography. So cryptography that is very efficient, especially when implemented over hardware devices with, let's say, constrained hardware resources, or low energy resources for hardware platforms for cryptography. Okay, so this is the motivation for using cellular automata. Now let's see what has been done about using cellular automata for implementing stream cipher, so the first type of symmetric cipher that I showed you. So let's go a little bit more in detail about the model of stream cipher that I was telling you about before, a few slides earlier. So the idea here is that you have this, this is called the Vernam stream cipher, because the Vernam cipher is basically the model of the one-time pad, which is the only stream cipher for which you can actually mathematically prove that it is unconditionally secure. So if you have a plain text and then you have a key that is as long as the original plain text, and this key is completely random, then you can prove that by computing the bitwise XOR to have the ciphertext, the adversary has basically no information by just observing the ciphertext of what is the corresponding message, what could be the corresponding plaintext message. So it is unconditionally secure because it does not use any computational assumption about certain, let's say, the hardness of certain computational problems, for instance. Here, on the other hand, we are kind of cheating because we are not using a key that is as long as the plaintext, or better, we are using it, but it is computed in a deterministic way using the so-called pseudorandom generator that we have mentioned earlier, right? So the idea is that we start from an initial secret key, which is truly random, let's say, and then we expand it deterministically using a pseudorandom generator. So at this point, we do not have any more unconditional security in terms of the original Vernam cipher. Actually, we have computational security because it all depends on the properties of the pseudorandom generator. If this pseudorandom generator is good enough, then you can see that for any reasonably computationally bounded adversary, it is not possible to actually predict what is the next, let's say, outcome of the pseudorandom generator, or even to invert it and get like the original key. How is this done with the cellular automata? How was this done like by Stephen Wolfram in particular in the 80s? So Wolfram, maybe you already heard about him, is, let's say, a guru of cellular automata. He's been also the inventor of Mathematica and Wolfram Alpha, all other host of nice computational algebra systems. And he has always been like kind of obsessed, or let's say like he studied a lot cellular automata. And in particular, in his studies also in the 80s, he proposed to use cellular automata to construct the pseudorandom generators in a Vernam stream cipher. What is the idea? Well, the idea is that you have a one-dimensional cellular automaton with periodic boundary conditions, okay? And you initialize these to the, so the seed of the cellular automaton is the secret key shared between Alice and Bob. And then you iterate for multiple steps like this cellular automaton, which is in particular equipped with the so-called the Rule 30. Rule 30 is, let's say, a convention adopted by Wolfram to index in an efficient way the local rules. The idea is that the local rules are simply Boolean functions, okay? So if you consider just the output of your truth table, so the set of all possible output values for each possible input combinations, then you have a string of bits, and then you can convert this string of bits into a decimal number. 30 is in particular the decimal encoding of that specific truth table for Rule 30. Okay, so the idea here is very simple. You use this cellular automaton equipped with Rule 30. You initialize the cellular automaton to the secret key of your stream cipher, and then you continue to iterate your cellular automaton until you have done like a number of steps, which is as long as the number of bits in your plaintext, okay? And then you sample only the trace of the central cell, for example, and you use this as a key stream. This key stream is then used as a key stream Z here that is bitwise XORed with your plaintext. So very simple, decryption works completely symmetrically, because if you perform again the XOR of your ciphertext with the same key stream, so Bob on his end will have to recompute the cellular automaton starting from the same secret key, then he will get the same key stream, and then by computing the XOR, since it is a symmetric operation, it is an idempotent operation in particular, it will get the original plaintext. So this paper actually got published in Crypto in 1985, and Crypto is like, let's say, the top venue in cryptography. So apparently in the 80s, like they were popular enough also among cryptographers to grant like publication in a top venue of cryptography. What happened, however, like a few years later, like at the beginning of the 90s, there were a couple of papers that showed that this pseudorandom generator proposed by Wolfram is terribly weak. In particular, Willy Meyer and Ottmar Steffelbach noticed that it is really vulnerable, this pseudorandom generator, to a so-called correlation attack, while Koch and Apwan showed a few years later that it is possible to approximate this pseudorandom generator by using like an affine approximation of Rule 30. So both these two attacks are exploiting the specific form of Rule 30. So Rule 30 is a rule of diameter 3. So each cell is looking at itself and the two right neighboring cells, as we have seen in the original example that I showed you for cellular automata. And this is the form of your local rule. So you XOR the leftmost cell, x1, and then you compute the OR, the logical OR of x2 and x3, so the two right neighboring cells. This allows basically to rewrite the rule in a certain way, such that instead of having, let me see if I can maybe write something I don't know if you can see it, but yeah, I can just do right here on the wall. But well, the idea is that when you have the initial condition, the secret key of your cellular automaton, and then you iterate it for several time steps here, the adversary is just seeing, let's say, this, in the sense that when he sees, for example, a ciphertext, and then for some other reasons, like he knows also what is a corresponding plain text in a setting that is called the non-plain text attack, then he can retrieve at least this column here that has been used, so the original key stream, okay? Now, if his objective is to find like the original secret key here, so the initial condition of the cellular automaton, well, if he does not know anything, then he needs to, let's say, if you have n cells here, he needs to guess at most 2 to the power of n possible secret keys, right? Which is exponential in the size of the secret key. So it would look nice. However, by the specific form of rule 30, if he knows this specific part here, then he can just guess half of the seed here. Then he will, let's say, compute forward like this part of the cellular automaton, just the right triangle. And then it will recover, due to the fact that the rule there is partially linear, it can reconstruct this left triangle here as well. So basically here, the idea is that once you have computed this right triangle, you check whether the left triangle is consistent, because of course, if you do not get like the correct seed here, then it might be the case that here you're getting some inconsistencies, okay? So you can just guess half of the seed in Wolfram cellular automaton. Worse than that, due to the specific properties of rule 30 that we will see in a minute, basically the problem is that not only you can just guess half of the seed, you can actually do, let's say, more sophisticated shortcuts by exploiting the correlations that are inside rule 30. And on the other hand, for Cocker and Apoan, it was a different kind of attack, but the idea was that root 30 can simply be approximated quite well by a linear function, and linear functions, you can predict them quite easily by using linear algebra, basically. So the consequences is basically that Wolfram's PRNG is basically useless when you instantiate it using root 30, because it is very weak, unless you use like very large keys, but that is not really practical. And after that, what you can see in the literature is that like papers about cellular automata, Wolfram PRNGs and stuff like that are not published anymore in crypto, in Eurocrypto, or in those nice crypto venues. They continue to be published like in cellular automata venues or in network computing venues. So apparently there seems to be like some kind of prejudice, or not exactly prejudice by cryptographers, but like saying, okay, we have already seen these kind of things before. We know that it is snake oil, so be done with it, and let's try something. Let's accept some other type of paradigms for publications. So what is the problem with what Wolfram did in his approach? The problem is that Wolfram basically used only empirical and statistical tests to say, okay, look, this is a secure pseudorandom generator. Why? Because you say, okay, if it is passing some statistical test, then you can say that it is not showing any specific pattern in the output, and so it is difficult to predict, right? The problem is that in cryptography, they learned it like the hard way during the 70s and the 80s, like with a lot of other botched designs, that statistical tests are not sufficient condition to say, okay, this is secure. They are just necessary conditions. So the first shortcoming that was initially adopted by, let's say, featured in the work of Wolfram, and then it was also present in subsequent works about cellular automata-based crypto, is that if you ground the security of your cellular automata-based primitive just on the basis on top of statistical tests, it can be misleading. It can mislead you in believing that it is secure while it is not, as is the tale of Wolfram's PRNG. So what is a corresponding insight for this shortcoming that I learned, let's say, also somehow the hard way during my PhD and subsequent research? Well, the fact is that statistical tests, they are fine, but you can use them only as necessary conditions. So you can use them to filter out the the width, let's say, from the width. So you can basically filter out bad cryptographic primitives. On the other hand, if you want to have like some more guarantees about the security of your cellular automata-based primitive, then you also need to consider the so-called cryptographic properties, at least of the local root, so of the Boolean function that is determining the next state of your cells. So the question now is, how can we salvage, let's say, Wolfram's PRNG? So here I need to do like a small detour about how stream ciphers are actually modeled and designed in, let's say, traditional cryptography, not based on cellular automata. And one basic building block here is the so-called linear feedback shift register, which is simply a device where you have like a set of registers here that are like every time that you are clocking the device, they are shifting one place to the left, okay? So what you see as an output is always what is shifted from the leftmost register here. And then you update the rightmost one with the feedback that is given by this linear recurrence here. So basically here you are computing, if you have, this can only be, this A0, A1 up to AK minus 1 can only be 0 or 1. So if it is 0, then you are not summing the corresponding flip-flop. Otherwise, you are summing it using an XOR, okay? So you update the rightmost flip-flop using this specific linear recurrence. You cannot use this directly as a stream cipher, as a pseudo-random generator for stream ciphers, because if you already see enough consecutive bits of the key stream, as, for example, by using a known plaintext attack, then you can basically recover the LFSR initialization, so the secret key, by using the Berlekamp-Massey algorithm, which is just based on linear algebra, let's say. So a more sophisticated model is the so-called combiner generator, where you have n linear feedback shift register. You clock them in parallel, okay? And then each of their output is then fed as an input to a Boolean function, f, and then the output of this Boolean function at each clock step will be the next bit in your key stream for your stream cipher. The nice thing about this model is that basically you can reduce like a lot of the security properties of this stream cipher just by studying the security properties, the cryptographic properties of this combiner function here. In particular, well, before going into the security properties, another example just to give you another idea. Instead of having n linear feedback shift register and then you combine them with a combiner Boolean function, you can have a single linear feedback shift register, and then instead you are filtering it using a Boolean function. So here you are tapping all flip-flops instead of just the leftmost one. And then you use this as a kind of a sieve, so this Boolean function f here, and the output of this Boolean function will be the next bit in your key stream. So it works exactly as the combiner model with using n copies of the same linear feedback shift register, but attacks, so also properties of the filter function here, are working a little bit different. In any ways, like be it the combiner generator or the filter generator, the important thing is that here you need to focus on the properties of the Boolean functions that you're using, either as a combiner or as a filter. So a Boolean function is basically just a, let's say, a mapping from, let's say, the set of n bit strings to the set of a single output bit, let's say. And you can usually represent it by its truth table, like we have already mentioned earlier, right? So you have, for instance, here 3 input variables. And then for each possible 8 combinations of the input, you get what is the corresponding output value, like 0 here, for example, in correspondence of 000, 1 for 001, and so on. And you can have, like, you can choose independently, like, each of these output bits. And then you have also another nice, unique, let's say, characterization or representation of Boolean function, which is the so-called Walsh transform. This is a kind of a discrete Fourier transform, where instead of, like in Fourier transform, like when you do signal analysis, what you want to do is to represent like your signal instead of the domain of time. You want to represent it in terms of frequencies, right? So you have like periodic functions, and then you want to construct like a basis using these periodic functions that are representing your signals as linear combinations of these periodic functions. This is the general idea. The general principle applies also here for Walsh transform, but instead of having periodic functions, you have linear functions. So linear functions are simply those of this form here, where you are computing an XOR of the input variables. So XOR is a linear operation, okay? And then each Walsh coefficient will tell you what is the, let's say, correlation of your function f with the corresponding linear function a dot x, where a is simply a vector of 3 variables in this case. So for instance, if you see here, this column here, so here you have the Walsh coefficient in correspondence of the linear function that is determined by the vector 0, 1, 0, which means that you are just considering the projection on the second variable, okay? So here you see that the corresponding Walsh coefficient is 0. It means that your function is completely uncorrelated with your linear function 0, 1, 0, okay? Of course, you would like ideally that it is completely uncorrelated with all linear functions, because if it is correlated with linear function, this is bad for certain attacks like linear cryptanalysis, okay? There are like mathematical reasons, of which we are not going into the details, why you cannot have like 0 everywhere here. There is like Parseval relations. There are a lot of other mathematical reasons why you cannot have that. So the idea is that here you want to juggle with the truth table of your function, such that you have a Walsh transform or a Walsh spectrum down here, such that the correlations with all linear function is as small as possible. So this will be, let's say, your cryptographic properties for saying that your function have a high nonlinearity. Having a high nonlinearity being means that basically these functions are as much as uncorrelated as possible with linear functions, okay? Then the function also need to be balanced. It means that you need to have like an equal number of zeros and ones in your truth table. It needs to be correlation immune of high order t, which means that basically if you fix, let's say, up to t variables inside your input, then the output must be statistically uncorrelated with the input. So there must not be any statistical correlations between input and output. So you have a bunch of these properties here. And now, how do we apply this to come back to Wolfram pseudorandom generator? Well, the problem of rule 30 in particular is that it is too small, because it has a small diameter of just 3 cells, to ensure any of those meaningful cryptographic properties that we have reviewed earlier, okay? So later works considered rules of larger diameters in there. So you have the number of possible rules of diameter d is 2 to the power of 2 to the power of d, because the length of a truth table is 2 to the power of d, where d is your diameter. And then you can set each output bit to either 0 or 1, so 2 to the power of 2 to the power of d. So this is super exponential, which is bad in the sense that until you have like d up to 5, you can do like exhaustive search. Other than that, then you need to resort to heuristics to find like Boolean functions that have a combination of good cryptographic properties. So here, for example, one of the first works that I did, actually my first work that I did with Alberto, right before starting with my PhD, was to consider like the set of Boolean functions that are so-called bipermutive. This means that your function, you can, yeah, I'm sorry that maybe it's a little bit confused, but maybe I will really go here. I'm really tempted. The idea for a bipermutive Boolean functions is that you have an XOR of the leftmost input variable plus a function of the central variables, okay, plus the rightmost variable. So you are XORing the leftmost and the rightmost, and then you are XORing it with a function of the central variables. This means to be bipermutive. What we have showed in this paper is that basically these functions satisfy first-order correlation immunity. So one of those nice properties that you want to have in your local rules for cellular automata-based pseudorandom generators. And then we explored like the set of all Boolean functions of diameter 5, in this case, which can still be exhaustively searched, in order to find those that were both, let's say, not only first-order correlation immunity, that you already have it theoretically because of bipermutivity, but also that they satisfy second-order correlation immunity, and also the nonlinearity as high as possible. So we have filtered them, and after filtering them, we subsequently applied statistical test to filter out those that were acting as bad generators with Wolfram's PRNG. And these were the last three that you can see here. So this is the dynamic evolution starting from an initial condition where you have just a single one in the center of your vector. And then you continue to see like what is the corresponding pattern. So these were passing all statistical tests coming from a standard suite from the NIST, the National Institute for Standard and Technology. Of course, this does not mean that you can still use these because maybe they are still, let's say, vulnerable to other types of attacks. But still, at least it is considering some cryptographic properties more than just what Wolfram did. So what is the shortcoming here? The shortcoming is that if you are considering, let's say, cryptographic properties for your local rules, this is good, but the properties is that the problem is that as we have seen, these properties are tailored only for some PRNG models. So the combiner model, the filter model, and the problem is that Wolfram's PRNG is not among, so it is not equivalent to a combiner or a filter generator. Okay. So there are two things here for the shortcoming. The first one is that attacks on the combiner or filter model maybe are not relevant in Wolfram PRNG setting, which is good. But the bad thing is that also cryptographic properties studied for the combiner and the filter generator and the filter generator might not capture, let's say, might not model other attacks that are just unique to the CA model, to Wolfram's model. So here the insight that I got is that you should like link the CA model that you use for generating pseudorandom numbers or pseudorandom sequences with the security properties and also related attacks that maybe are different from, they work in a different way from the combiner and the filter model. Maybe some of the properties such as correlation immunity are still relevant. And in particular for Meyer and Staffelbach attack, this was exactly the case. So those shortcuts that I was mentioning a few minutes earlier, that you can use here not only to guess the alpha of the seed, but also to just say, okay, not all seed are equally probable, let's say. This depends from the fact that rule 30 is not first order correlation immune. If you have something that is first order correlation immune, like the rules that I showed here, then some of these shortcuts the attacker cannot apply it anymore. So somehow there is some relevance of these properties, but still it should be better linked, let's say, to the CA model, this type of research. Now, to go a little bit quicker on the part of block ciphers, because here we don't have a lot of, so there is a lot of works, but actually this part has been like researched by cryptographers much more than the stream ciphers based on cellular automata. So this is just to give you a bit more of an idea of how SPN block ciphers work, in the sense that you have like here, as we said, these confusion layer and then the permutation layer, also called the diffusion layers. And confusion and diffusions are, let's say, abstract principles that were set forth by Claude Shannon back in the 40s to say, okay, every iterated cipher should satisfy good confusion, which means that the relationship between the plain text and the ciphertext and the encryption key must be as complicated as possible for the attacker to find out. This is confusion. Diffusion means instead that the statistical structure of your plain text is spread, let's say, from the onto the ciphertext. Okay, so you have something that is randomly looking, let's say. So if we focus on the confusion layer, then here you see that the plain text block is in turn, let's say, processed by small building blocks. There are S boxes. These are simply vectorial Boolean functions that are mapping n bits into n bits, okay? And again, these vectorial functions or S boxes, substitution boxes, must satisfy several properties, similarly to what we have seen for pseudorandom generators with Boolean functions. So they need to be invertible because otherwise you cannot retrieve the ciphertext and this will be kind of useless. They also need to be highly nonlinear in order to resist to linear cryptanalysis, and they need to have like a low differential uniformity, which is a property related to differential cryptanalysis attacks. So there are two ways here to use cellular automata for block ciphers. The first one is what I call the dynamical system way, where you say, okay, you have a cellular automaton, then you iterate it for multiple steps, And then you use the entire configuration of the cellular automaton instead of just the trace of a single cell as a, let's say, ciphertext block. So the final configuration will be the ciphertext block. So this is typically seen in publications that have appeared in cellular automata venues, so not in cryptography-related venues. And they have like several weaknesses, as we will see in a moment. Otherwise, you have the so-called reductionist way. This is used a lot by cryptographers. For example, Johan Demen, who is one of the inventors of the AES standard encryption algorithm. He used like a lot of these, not in AES, but in other designs, he used like a lot of these approaches based on cellular automata to design new ciphers. So the idea here is that instead we are iterating the cellular automaton for a single time step, okay? And then you're using it to encrypt just a part of the plaintext, of course. And then you are interleaving it with other type of operations that are not based on cellular automata. So what is, just to give you the idea, the dynamical system way for designing these block ciphers? So the first work here in this line was given by Gutowitz, who said, okay, I'm iterating a cellular automaton as a dynamical system. And then I'm doing like for confusion, I'm using an iteration of a so-called partition cellular automata, which is reversible, okay? For diffusion, instead, you use like a way to compute pre-images in by permutive cellular automata, so the same type that we have seen before for stream cipher based on cellular automata. So the idea is that you have your plaintext here, and then you compute a pre-image of your cellular automaton, which will be larger in this case. So we are in the no boundary setting in this case. So you can do this because bipermutivity allows you to say, okay, if you just say that you know a small block of size d-1, where d is your diameter, then you can use left permutivity and right permutivity to, let's say, complete the rest of the pre-image, okay? And then you continue like this until you have your ciphertext, which will be larger in this case than your plaintext. Okay, so this is for diffusion. For confusion, Gutowitz used reversible cellular automata. The problem here is quite simple, that so far, and this was like published in the 90s, there have been no formal security analysis of this model here. And well, there is a reason. The reason is that cryptographers usually do not like this kind of non-standard paradigms, because this does not correspond to the SPN cipher that I showed you before, because it is more difficult to analyze their security and to analyze attacks on these kind of paradigms. So the shortcoming here is that using non-standard paradigms can be a hindrance to design block cipher based on cellular automata. And you see a lot of publications that are still doing this and then saying, okay, yeah, but this has like a good confusion and diffusion, but like citing it like at a very general level, at a very shallow level. You say, yeah, it is like very confused here, like the ciphertext, it is very diffused. Maybe they compute some metrics about it, but this is definitely not enough, and it is not a sound approach. On the other hand, cellular automata are simply vectorial Boolean functions, as we have seen. So it is preferable to work with well-established paradigms, such as SPN ciphers or sponges, which is like another type of paradigm for block ciphers. And then we insert inside these paradigms, these designs, lower-level building blocks based on cellular automata. For example, S boxes that we have seen earlier. So to give you an idea, in the Ketchuk construction that is actually become the standard for the NIST SHA-3 hash function, you have actually a cellular automaton which is well hidden within the design of the cipher of the hash function in particular. So you have a cellular automaton with periodic boundary condition with 5 cells in this case, that is based on this specific local rule here, which is rule 210 in Wolfram's naming convention. The important thing here is that this part, this cellular automaton, is computed for a single time step, and then the rest, like for diffusion and so on, it is interleaved with other non-local transformations, so operations that are not based on cellular automata. So there are other works following this idea, just focusing, for instance, on designing S boxes based on cellular automata. You could again see like the algebraic approach, where you are considering specific rules for the CA, and then you analyze the properties of these specific rules, such as being done, for example, in the case of Ketchak. Otherwise, there is a more general heuristic approach where you use like optimization algorithms such as genetic programming, genetic algorithms, and so on, to optimize, for example, both the cryptographic properties of cellular automata as boxes, and also other properties such as low implementation cost. For instance, genetic programming is nice because it is like representing your local rule simply as a tree, okay? And this tree is a good proxy for the complexity of the circuit of your overall cellular automaton, okay, of your whole cellular automaton. So it is a good proxy to understand, like, basically it is saying the smaller is your tree here that is evolved by genetic programming, the more efficient can be implemented your local rule in hardware, for example. Now, a last remark is whether we can use cellular automata in the design of a block cipher for everything. So for doing confusion, okay, we have seen it, confusion we can construct S boxes in quite an efficient way, which is good. And many of those works actually have been published also in cryptography-related venues. So there is more connection between the cellular automata and the cryptography communities. On the other hand, for diffusion, actually, cellular automata simply suck because, yeah, you can see here, for instance, this is an example taken with rule 45. The problem is that diffusion is related to the speed to which like differences are propagating in your ciphertext, okay? And the problem is that with cellular automata, the speed at which these differences can propagate is bound by the diameter. So the so-called speed of light is called in the cellular automata terminology, which is determined by the diameter. So here, if you insert like a difference at this point of your input, then this will, let's say, propagate very slowly because it is bounded by the diameter of rule 45, which in this case is 3. So it can only get, let's say, 2 cells across, like in a single time step. And the problem is that here diffusion, when you want to design like a, let's say, an efficient block cipher, so diffusion needs to have like quick propagation characteristics. So the final shortcoming is that like cellular automata are just bad for implementing like diffusion layers. And a further motivation here to work with well-established paradigms such as SPN ciphers is that for certain components of block ciphers, so you can just abandon the cellular automata approach. This has been done, for instance, in Ketchak, where in the diffusion phase, the designers of Ketchak were using like non-local transformation that cannot be described by a cellular automaton. And in that case, one could still be left with the nice research direction of saying, okay, if I still want to research to study diffusion layers done with cellular automata, how many iterations do I need in order to get like good difference propagation characteristics? So if you see it here, if you use like small cellular automata rules, then they are definitely bad because you will need a lot of iteration before the differences are propagated to the whole state, okay? On the other hand, you could say, okay, I could consider like a larger diameter. I could consider a diameter which is as large as the state of the cellular automaton. This is also done, although you cannot like apply it for very large states. Like this is done, for instance, with S boxes, having a diameter which is as large as the size of the cellular automaton. But usually there you have at most 8 bits in your cellular automaton state, so you can still do that. Here instead, if you have 128 bits, it becomes a little bit more complicated to implement it in an efficient way. But maybe you can investigate some trade-off between like larger diameters and let's say a certain size of your CA state. And yeah, so to conclude, so to sum up, cellular automata are definitely useful, so they are not to be completely discarded for cryptography, because as we have seen, cryptographers actually use them in standard in real-world designs for ciphers, hash functions, and so on. But there is like the, let's say, strong need to link their properties to security models and properties that are relevant for the design of ciphers. So the problem of the disconnection between like the cellular automata community and the cryptography community is that the properties that are studied by people in the cellular automata community, such as, for example, dynamical system properties, chaos theory, these kind of things, they do not relate in a nice manner to properties that are actually based on, that are used in cryptography. So for instance, Wolfram was saying, yeah, rule 30 is a good rule for my pseudorandom generator because it has like chaotic properties. And it is actually true because you can formalize it using the tools of chaos theory, showing that that rule there, it is inducing like a dynamical system which is strongly chaotic in the sense of defined by Devaney. The problem is that this strong chaos property is not enough for security in cryptography. So the fact that you have this butterfly effect, for instance, in this cellular automaton is not enough for, let's say, preventing an attacker to actually break your crypto system. And a couple of directions for future research. So in the case of stream ciphers, the necessity there is to closely analyze the pseudorandom generator set forth by Wolfram, and in particular to study new attacks that are specific to this model here, that are maybe not applicable to the combiner or the filter generator. And for block ciphers, on the other hand, one idea that I've already mentioned is to study permutation or diffusion layers based on the design of cellular automata and compare them with traditional ones, like to see if you can really gain or at least match the same performances of non-local transformation with cellular automata. And that's it. So thank you very much for your attention. And if you have any questions, feel free to ask. Thank you.
So thank you. I have no experience with the cellular automata, so sorry for the question is done. But
no worries.
Looking at the attack on Rule 30, it looked like kind of ad hoc attack.
Yes.
Okay. So I was also wondering, considering also the property of speed of light, if you're aware of any family of attacks, let's say, that exploit this limit in the growth of this.
That's an excellent question. Actually, I'm not aware of those, at least not in the, for sure, not in the works that have been published in cellular automata venues. Probably there is something related in some cryptography papers where they use like similar models, but the problem is that there they are always interleaving with something that is not like a cellular automaton. So there are like a lot of theoretical bounds, like on the attacks that you can do like with differential cryptanalysis. And for instance, like some of the phases there are also using cellular automata-based designs. But like for a pure cellular automaton, no, I'm not aware of this. Okay.
Okay, if there are no other questions, we thank the speaker again.
Thank you. Thanks.